Hello friends, welcome to my channel. This is Objective Mechanical Part 7, useful for BEL, State PSC, IAS, PSU and SSC JEE examination. This is also useful for RRB examination. Question is, two plane slabs of equal area but with thermal conductivity in the ratio 1:2 are held together with temperature between the two outer surfaces being T1 and T2 if the junction temperature between two surfaces is desired to be T1 plus T2 by 2, then their thickness would be in the ratio of thickness we have to calculate. Two plane slabs of equal area. Let two slabs thermal conductivity K1 and K2. K1 for slab 1 and K2 is for slab 2. Temperature between two outer surfaces. Let here temperature is T1 and here T2. Let interface temperature is Ti. Thickness of first slab is L1. Thickness of first slab is L2. Thermal conductivity is in the ratio of 1:2. So K1 by K2 1 by 2. And junction temperature Ti is T1 plus T2 by 2. We will apply Fourier's law of heat conduction. So in both slabs, heat transfer rate is same. So Q1 equal to Q2 K1 A1 dt by L1 K2 A2 by L2. Area is same given in the question. So K1 here, this side temperature is T1, T2, interface temperature is Ti. So dt is T1 minus Ti divided by L1 K2 Ti minus T2 divided by L2. So K1 by K2 ratio is 1 by 2. So 1 by 2 into T1 minus interface temperature is T1 plus T2 by 2 divided by L1 equal to T1 plus T2 by 2 interface temperature minus T2 by L2. We have to calculate L1 by L2. So half into 2T1 minus T2 by 2 divided by T1 plus T2 minus 2T2 by 2 L1 by L2. So 2 cancel. Then if you solve this one, L1 by L2 equal to 1 by 2 into 2T1 minus, this is T1, T1 minus T1, so T1 minus T2 divided by T1 minus T2. It will cancel. L1 by L2 equal to 1 by 2. to 1 by 2. So from option we have to check 1 into 2. A is our answer. This type of question they are asking in IS, GATE, BEL also. This type of question they will ask. Question is thermal diffusivity of a substance is thermal diffusivity. It's alpha heat conducted divided by heat stored. Or heat conducted. This definition of also important. Heat conducted by heat capacity. And mathematically alpha equal to K by rho Cp. This is also very important. Its unit also important. Meter square per second. So from here alpha is inversely proportional to 1 by Cp. This question, thermal diffusivity of a substance is inversely proportional to the thermal conductivity. This is K. So alpha is directly proportional. So this is not possible. Directly proportional to the density of the substance rho. Density is inversely proportional, so this is also not possible. Inversely proportional to the specific heat. This is Cp. This is correct. Directly proportional to the kinematic viscosity. This one not related. So C is our answer. This type of question they are asking in ISRO, IES and BEL also. They will ask this type of question. So this is very important. This one, thermal diffusivity is the ratio of heat conducted by heat stored. This mathematically then its unit. This type of question they asked in GATE 16 or 15, not sure. They asked this type of question. If the temperature of a solid surface increases from 27 degrees Celsius to 627 degrees Celsius, its emissive power increases in the ratio of, so T1 is 27 degrees Celsius in Kelvin, 300 Kelvin. T2 is 627 degrees Celsius. In Kelvin it's 900 Kelvin. So emissive power is sigma A Ts to the power 4. So E is proportional to T to the power 4. So E1 by E2 you have to calculate. E1 by T1 to the power 4 equal to E2 by T2 to the power 4. E1 by E2 equal to T1 is 300 divided by 900 whole to the power 4. So 1 by 3 power 4. 1 into 81. So D is our answer. It is desired to reduce the radiation energy exchange between two infinite parallel planes by inserting radiation shields of the same emissivity. The number of shields required for 80% reduction will be how much? The number of shields required, a direct formula is there. Heat transfer, radiation energy exchange with shield divided by radiation energy exchange without shield. Without shield. Its formula is 1 by n plus 1. N is number of shields. So in this case, required for 80% reduction. So Q with shield 80% reduction. So 1 minus 80 by 100. It will come 0.2. So Q shield is 1 and this is without shield. Q without shield is 1 and Q with shield is 0.2. So here you put Q shield divided by this is 0. Let it be Q without shield. You take it Q and here 0.2 Q. So Q with shield is 0.2 Q divided by Q is 1 by n plus 1. So 2 by 10 plus 1. 1 by 5 equal to 1. So n is 4. Number of shields required is 4. Directly also we can solve 0.2 by 1 by n plus 1 n equal to 4. Only thing is you have to check this one. What is the percent of reduction? Fins are provided on heat transferring surface to A. Increase surface area to promote the rate of heat transfer. B. Increase temperature gradient so as to enhance heat transfer. Increase turbulence in flow for enhancing heat transfer. Decrease the pressure drop of fluid. A is our answer. Increase surface area to promote the rate of heat transfer. If the radius of any current carrying wire is less than the critical radius, then the addition of electrical insulation will enable the wire to carry a higher current because this type of question I already solved in ISRO solution for heat transfer. You can check it from my playlist. Two graphs are very important, I already told. Heat transfer Q versus outer radius. Here thermal resistance versus radius. So the graph is like this. It will increase after some time. It will decrease. Here also it will come like this. For conduction it will increase gradually, and for convection it will decrease little bit. Here that critical point will come. This figure here it will come. RC critical, here RC critical. This is R1, here this is R total conduction, thermal resistance for conduction, here thermal resistance for convection. This is also very important. Sometimes they are asking for convection and sometimes they are asking for conduction. R total also sometimes they are asking up to critical radius. R total will decrease and after critical radius it will increase. Here in this case, below critical radius heat transfer rate will increase and after critical radius it will decrease. So up to this region R1 to RC, this region we are using for wire, because in wire we want more heat transfer, and beyond RC this area we are using for pipes, because in pipes we don't want heat loss. So in this question, addition of electrical insulation will enable the wire to carry higher current, because here in this region it will come, because addition of electrical wire less than critical radius. So here it will come in between R1 to RC, which is Q maximum heat transfer at RC point. Then here thermal resistance of the insulator is reduced. Here it's reducing, but which one they are telling, that is not confirmed. Total thermal resistance or for conduction or for convection. Thermal resistance of the insulator is increased. If it is conduction, then it will increase. Not mentioned, so this is not possible. A also not possible. Heat loss from the wire is reduced. It is in this region, so heat loss is increasing. C also not possible. So our answer is heat loss from the wire is increased. This is also very important. So many times asked in various exams. So both graphs you should know. R2. This graph also very important. Convection, thermal resistance for convection it will decrease, and for conduction it will increase. And up to critical radius heat transfer will increase, and beyond critical radius it will decrease. Beyond critical radius we are using for pipe flow, and before critical radius we are using for wire. An ideal observer of radiation is also an ideal emitter. It is known as, its answer is Kirchhoff's law. Kirchhoff's law definition is the emissivity of a body is equal to its absorptivity when the body remains in thermal equilibrium with its surrounding. Is equal to absorptivity alpha. From Kirchhoff's law, Wien's law, lambda into T is constant. Planck's law for black body radiation. Question is, a thin flat plate is hanging freely in air at 27 degrees Celsius. Solar radiation falls in one of its sides at the rate of 500 watt per meter square for maintaining the temperature of the plate constant at 32 degrees Celsius. The value of heat transfer coefficient is how much? H value we have to calculate. Thin flat plate hanging freely in air at, so T infinity is T7 degrees Celsius. Solar radiation falls Q by A watt per meter square. Plate temperature Ts is 32 degrees Celsius. From Newton's law of cooling, Q equal to HA Ts minus T infinity. We have to calculate H, heat transfer coefficient H. H equal to Q by A into Ts minus T infinity. So Q by A given 500 and Ts minus T infinity 32 minus 27, it's 500 divided by 5, it's 100 watt per meter square. Unit also important, sometimes they are asking unit. So C is our answer. This question is very, very important. Nusselt number for free convection and for free convection or natural convection or for forced convection. So both values we have to know. Nusselt number is a function of Reynolds number and Prandtl number for forced convection. So it's very, very important for all exams. Even if GATE also they are asking this type of question. Nusselt number is a function of Grashof number and Prandtl number for natural or free convection. Or we can write it as it's a function of Rayleigh number for natural or free convection. LMTD of a heat exchanger with delta T1 and delta T2 being temperature differences between the hot and cold fluids at entrance and exit respectively. If you will take this type of questions also, I already discussed in heat transfer papers. Quick review also I did. If it is a parallel flow heat exchanger, temperature of hot fluid at inlet, temperature of hot fluid at exit, temperature of cold fluid at inlet, temperature of cold fluid at exit. This is, for example, I am taking this one, parallel flow heat exchanger. So in this case, delta T1 is THI minus TCI, and delta T2 temperature difference at exit is delta THE minus TCE. For problem solving, all public sector exams they are asking this type of questions. You have to remember that log 2 value also. It will be very useful. You have to remember that one. So LMTD it will come delta T1 minus delta T2 divided by log delta T1 by delta T2. So from option Here also we can write it as delta T2 minus delta T1 divided by log delta T2 delta T1. So from option A is our answer. Thank you friends. Thank you for watching my video. Thank you.